Welcome to The Explainer. So today we are diving headfirst into one of the absolute biggest breakthroughs in modern tech. If you've ever used ChatGPT or, one of those scarily accurate translation apps and thought, what is actually going on under the hood here? Well, you are in exactly the right place. We're going to completely demystify the core architecture that is single-handedly powering this entire AI boom. We're talking about the transformer. It is a wildly fascinating journey that completely changed how machines process information, so let's just jump right in. Now, to really grasp why this tech is such a game changer, we actually need to step back and look at a fundamental philosophical problem. As Nobel laureate Herbert Simon pointed out in the foreword of our source material, attention is the most valuable resource of the information economy. Think about it. In a world where we are just drowning in an absolute overabundance of information, the real challenge isn't getting the data, right? It's knowing how to efficiently allocate our attention to find what actually matters. And as you'll see, this exact concept, efficiently allocating attention, was the secret sauce that helped modern AI finally conquer its biggest limitations.
Which brings us to Section 1, AI's memory bottleneck.
Okay, so to appreciate the cure, we really need to understand the disease. If we look at the history of AI, neural networks aren't exactly a new idea. Way back in the 1940s, we had the McCulloch-Pitts neuron, which essentially simulated intelligent behavior using basic threshold logic. Fast forward to 1986, and we get a massive leap with backpropagation. This is what allowed multi-layered neural networks to actually learn complex patterns. But when it came to processing sequences, things like human language, we were stuck relying on recurrent neural networks, or RNNs, for a really long time. They were the absolute standard right up until 2017. That's when Google dropped a paper famously titled Attention is All You Need, introducing the transformer architecture. But why was a totally new architecture even necessary in 2017?
Well, let's think about how an older recurrent neural network actually worked. Say it's trying to translate the French phrase j'aime le thé. In an RNN, the network has to process the words sequentially, one step at a time. The fatal flaw here is that the system is forced to compress the entire meaning of that input sentence into a single, fixed-length state. They call it a context variable, or context vector, right at the end of the encoder. Imagine trying to compress an entire paragraph, or, a whole book, into one single variable before you can pass it over to be translated. It's ridiculous. That single vector becomes a massive, crippling bottleneck. And this bottleneck created some really severe issues. First off, as your input gets longer, you inevitably lose long-term information during all that compression. The AI literally forgets the beginning of a long sentence by the time it reaches the end. It's like trying to remember a really long phone number and forgetting the area code. Second, RNNs suffered from what we call vanishing and explosive gradients, which just makes them incredibly difficult to train on long sequences. And finally, and this is a big one, because RNNs have to process data sequentially, they are incredibly difficult to parallelize. You couldn't just throw more computer chips at the problem to process a whole sentence all at once. Bottom line, they were slow and they were forgetful.
So how did we fix it? Let's move to Section 2, the psychology of attention.
So how exactly do you solve a bottleneck caused by information overload? Well, you look at a system that's already perfected it. Biology. Get this. The human optic nerve receives information on the order of 1 billion bits per second. 1 billion! But our brain's actual capacity to process that data is far, far less. If our brains tried to process every single bit of that sequentially, just like an old RNN, we would literally freeze up and crash, like an old laptop with way too many browser tabs open. Thankfully, our brains are expert filters. To survive, we use visual attention to focus only on specific, relevant stimuli, and we just filter out the rest of the useless noise. The 19th century psychologist William James actually created a brilliant two-component framework to explain how we do this. He separated our attention into non-volitional and volitional cues. Non-volitional cues are entirely involuntary. They're based on the saliency or how much something stands out in the environment. So if a baby suddenly starts crying in the next room, your attention is hijacked immediately, right? That's non-volitional. A volitional cue, on the other hand, is voluntary, deliberate. It's you actively choosing to focus your attention on reading a specific book because you're trying to find an answer to a problem. You are in the driver's seat directing your focus.
And this perfectly sets up Section 3, queries, keys, and values.
This is where it gets really fun because we can actually bridge the gap between human psychology and the math driving the AI revolution. We can map William James's psychology terms directly onto the technical architecture of a transformer. The volitional cues, your deliberate effort to look for something, Those become the query. The non-volitional cues, the distinct, noticeable traits of the data, those become the keys. And the actual sensory inputs themselves, those become the values. The attention mechanism in a transformer acts as this incredible memory unit that brings all three of these elements together. So, mathematically, what is actually happening? The attention layer receives an input as a query, and it measures the similarity between that query and the available keys using a scoring function, which is typically a scaled dot product. It then computes these things called attention weights using a softmax function, allowing the network to output a weighted sum of the values. Okay, actually, scratch the jargon. In plain English, the AI basically compares what it's looking for, the query, with the labels of the data, the keys, to pull out only the exact information it needs to focus on, the values. And the absolute magic here? Unlike an RNN, the transformer computes these attention scores for all the words in a sequence simultaneously. It runs entirely in parallel. Boom, no more bottleneck.
And that breakthrough takes us to section 4, the transformer revolution. By solving that memory bottleneck and unlocking massive parallel processing, transformers didn't just improve AI a little bit, they completely blew the doors off the entire industry. And this architecture isn't just for translating text anymore either, because the attention mechanism is just so remarkably efficient at finding relationships in data, it is actively eating the entire AI world. For text, we got massive models like BERT and GPT-3, but it didn't stop there. In computer vision, we now have the vision transformer, or VIT. In speech recognition, there's Wave-to-Wave 2.0. We've got Timesformer for processing video, and graph transformers for insanely complex relational data. Just the simple act of teaching an AI how to pay attention to different parts of an input simultaneously, it has completely revolutionized every single one of these domains. It's wild.
But with all this incredible power comes a profound new challenge. As these multi-headed attention mechanisms grow increasingly complex, literally processing billions of parameters in parallel, how on earth do we tackle the critical challenge of AI explainability? The source text actually dedicates its entire final chapter to this exact issue. Because think about it, when an AI makes a critical medical diagnosis or a major financial decision, simply knowing that it paid attention to certain data points isn't really enough to build trust, is it? As these models become ever more capable, will we ever be able to fully unspool the mysterious inner workings of the black box? It is absolutely the vital question for the next era of machine learning. Thank you so much for joining me for this explainer, and definitely keep your attention focused on what comes next.